So the Rich Earth Institute in Vermont has been running a urine recycling program for the last few years. And the first portion of this program is going to walk through why we're doing this and what we're trying to accomplish. And then the second half gets more into the details of what we've actually done and where we want to be heading in the future. So this is a nutrient cycle on a farm. And this is, I think, what a lot of the people looking at sustainable agriculture are thinking about in terms of nutrient recycling, is just keeping things on the farm as long as possible. Nutrients come in feed and fertilizer, get cycled through animals, through plants. If you're running a sustainable farm, you cycle those back to the soil. But ultimately, you're selling products off the farm, and all of the nitrogen, potassium, phosphorus, and other minerals that soil fertility depends on are leaving the farm in your product, and then they're heading to our plates. So here's a slide that shows in this little grow section here, that's the whole farm. All that nutrient cycling is happening there, but we zoomed out, and the bigger picture is that chemical fertilizer is being produced using natural gas, using mined phosphate, non-renewable resources that are expensive to produce. Those are going to the farm, we're eating the product of the farm, excreting them, and those are going into the wastewater, where they are pollution that then needs to be pulled back out by a wastewater treatment plant, which is another, as you all know, expensive and resource-intensive process. So on both ends of this chain, we're using resources and consuming energy and potentially still causing pollution. Our vision is for an intact nutrient cycle where there is no beginning or end point, where there's no point that it becomes a waste, where the nutrients become pollution. This bottom step here says compost, but in our case it's a liquid sanitization step, but it allows us to cycle those nutrients right back into agriculture so there is no waste product. We have been working with urine for some very specific and compelling reasons, and these next charts are comparing urine and feces, their physical properties, and they're color-coded so you can keep them apart. This is just the wet and dry mass. Everyone knows there's a lot more urine than feces, no surprise, but on the right, the dry mass, even if you were to dehydrate urine and feces completely, you would still have much more solid matter from the urine. 2/3 of human waste is actually the urine on a dry weight basis. That was surprising to me when I first learned that. But even more surprising is the concentration of nitrogen in urine versus feces. You've got about 85–90% of the nitrogen from human waste is in the urine fraction, and for phosphorus, it's about 2/3. So urine really is where it's at in terms of nutrients, although people are very surprised to hear that typically because it seems like just this watery material that's just a little bit yellow and nothing to it, but it's where the nutrients are. So we focus on it. And how much nutrient is really in there on an absolute scale? The fertilizer in the urine a person produces in a day has enough fertilizing power to grow a loaf of bread worth of wheat. So every day that we use a toilet to flush away our urine, we're flushing away enough nutrient to grow an entire loaf of bread. So that's, in terms of the agricultural process, that's a significant amount of nutrients that we're talking about. Then if we look at the wastewater side of it, if we, instead of using it as fertilizer, continue to flush it down the sewer, what portion of the wastewater nutrient load are we talking about? And it's a large portion. So again, color-coded for your convenience, urine has 75% of the nitrogen that is in typical domestic wastewater or municipal wastewater, and 55% of the phosphorus. So if we were to remove the urine from municipal wastewater, keep it out from being in there in the first place, you'd be removing 75% of the nitrogen pollution problem, 55% of the phosphorus pollution problem. If you were to use toilets that kept all human waste out of the wastewater stream, we'd be looking at a combined 80–85% of nutrients being removed. And that's not by any nutrient removal at the plant. That's simply by keeping human waste out of the wastewater in the first place. And in our area, we're looking at eutrophication of lakes, but also of the coastal waterways. Here, I understand you're more concerned about the Great Lakes. This picture was Lake Erie several years back, and the overgrowth of algae caused by eutrophication from an overabundance of nutrients. So we got into this by looking at the fertilizer side, thinking it would be great to get this back to farms, but I quickly realized that it's really the pollution prevention that is the immediate crisis that this country is facing in terms of wastewater. And this is a radically different way to address that crisis from end-of-pipe solutions at the wastewater treatment plant. This slide gives a graphic comparison of the ingredients in wastewater. Wastewater is more than 99% tap water and less than 1% human waste. So that informs our work because the typical solution of conveying all waste by water carriage to a central plant makes sense with these large volumes, but if we remove a small fraction, the human waste, it actually becomes practical to separate it, store it, and truck it. You never want to truck all the waste from a building, but the human waste actually is a manageable volume. And that's just what we've been doing at the Rich Earth Institute. We have a program with close to 200 participants who have various kinds of systems they're using to collect their urine and bring it to a central depot where we can then begin these processes. And there are 3 places in our immediate region where doing this is very compelling. It's Long Island Sound, Cape Cod, and the Great Bay in New Hampshire. Those are places where there is mandated removal of nitrogen, particularly from wastewater, that communities are struggling to figure out how to do on a cost-effective basis. And this is a breakdown on, in the New England area of what it costs to remove nitrogen from mid-sized to small communities, on $1 per pound of nitrogen removed. And they're pretty high costs for some of these communities. Per pound of nitrogen, $200, $250, $270 on Cape Cod or the Great Bay of New Hampshire. And if you consider that a person produces 8 to 10 pounds of nitrogen per year, that means on a per capita basis, these towns are considering putting in systems that'll cost $2,000 to close to $3,000 per year per person just to remove the nitrogen from their wastewater. And by putting in some of the urine diversion systems that we've been considering, it's closer to $30 per pound for nitrogen removal. And there was an interesting paper we were just looking at from Cape Cod that looks at that and has somewhat different numbers for these, but still, the urine removal for nitrogen reduction is by far the most cost-effective solution. That's just what this slide says. But it says at the top, the avoided wastewater costs are greater than the fertilizer value of urine. That's what I was alluding to before. The fertilizer cost is great, but fertilizer nitrogen costs maybe $1 per pound, sometimes even less, to buy nitrogen fertilizer to use on your farm, whereas taking it out of the wastewater, it can be hundreds of dollars per pound. So we definitely want to see it go on to farms, but the folks who are going to be willing to invest in this technology are the ones who want to get the nitrogen out of their wastewater. So how do we do this? What do we do to achieve this process? This is what we've been doing on our pilot scale, just in terms of to get enough urine for research. We've been distributing, we have one right here. We've been distributing these handy containers made out of locally sourced, largely recycled ingredients. It's set up to be a portable, waterless urinal. You can put it anywhere in your garage. People have them in their bathrooms. I have one of these in my home. And the thing about it is, stored urine does not smell good at all. And so the first year we did this, we had people, as a labor of love, doing this and just going the extra mile. And then we realized these donors are not going to stick with us if they keep having to just do what they've been doing. So we designed this. It's got in the top a ping pong ball there. That's an automatic little float. So it floats up, allows liquid to go through, seals back down. They're wonderful. I have one in my bathroom. You can't smell it at all. It's just a lovely thing. But of course, it's not what we expect every person in America to be using. So one thing that men are very familiar with are these urinals, these waterless urinals. You have waterless urinals on campus, I understand, and it takes no change in user behavior. It doesn't even take user knowledge or investment to plumb these to a central collection tank where it can be then pumped, removed, and used as fertilizer. And then there are these urine diverting flush toilets, which are also a very short leap from what people are used to. It's a porcelain toilet. It flushes in the back, but in the front it has a urine collection basin that drains through a separate drain to a collection container. These are available in Europe. They're set up for the European standards, so it is a little bit awkward to retrofit them in the US, but they're a largely familiar system, even though you can see that it's a little bit different. And then this is even a further step toward complete nutrient reclamation. This is a dry urine diverting toilet. So again, the divided bowl, but the back part doesn't flush. It leads down directly into a solids collection chamber or a composting chamber. And this is just a photograph of the full circle composting toilet. This is something that before I was involved in the Rich Earth Institute, I still do it, but my main business was building these systems and installing them. It's a composting toilet where the solids will compost along with wood shavings, toilet paper, any other organic matter, and produce a sort of a neutral mulch-like compost that has the remaining phosphorus and nitrogen in it. So with this, you can get complete elimination of any liquid discharge to the municipal sewer system. And that's a pretty non-standard, unfamiliar sort of a solution, but it's something that all these solutions, the urine diversion and the dry composting, are both becoming more mainstream. This is the Green Plumbing and Mechanical Code supplement for the Uniform Plumbing Code, and it's a document that comes out every few years. They're called REACH codes. They're codes that are above and beyond what is required in the code and what would be practiced by most installers or plumbers, but it's things that through this code and through the governing body become allowed. So you don't have to do them, but you can show this to your local enforcement officers and say, look, it's in the code, we can do this. And that's something that urine diverting composting toilets are now part of the code for 2015. We were part of the rewrite process for that. We're very excited to have that be something that is brought a little closer to the mainstream. Nowhere near it yet, but it's on the way. So to recap, key aspects of the urine diversion, it can be low-tech or high-tech, anything from this to the systems we're going to talk about getting further in. It can be centralized or decentralized. In Europe, there's actually an encouragement of home use, and that's something we're not going to get into in this conversation, but a lot of people in Europe use this in their home gardens. We have heard from a lot of people in the US who do it as well, and there are very, very safe ways in terms of human health and environmental health to do that, and then you can do the more centralized things we discuss. Turns a pollutant into a resource and removes both phosphorus and nitrogen at the same time. And in places like Cape Cod, Great Bay, Long Island Sound, it's increasingly being seen by planners as a viable solution, a viable option to do this. So with that, I'll turn this over to Kim, who will talk about what we've been doing on our own particular project in Vermont.
Academics have known for quite a long time. You can find papers for more than 50 years that say we should be taking our human waste and returning it to soils. And so what we decided to do in Vermont was to just dive in with both feet and just start a project, because we really need pilot projects in this country to sort of demonstrate how this works. So this is our urine depot, and people come to this self-service pump that you see on the left-hand side in the blue, where they bring this and they take the cap off and plop that pump into this container and put it into the 275-gallon tank. And then our septic hauling company, who we have a great partnership with, they come, they pump the whole tank out, and they take it to our farms. And at our farms, we are permitted in Vermont to do 2 different kinds of treatment to the urine, so that satisfies the regulation, and to make sure that there's no fecal contamination in it. Because when you have these divided bowls, like we have one here, this is also an imported piece of plastic from Sweden, very expensive. Someone in the US needs to start making these. So this is a separate divider. So, where was it?
Potential for fecal contamination.
Yeah, because the bowl is divided, when you have the urine catchment, then sometimes you might have an accident, and so sometimes you get fecal contamination. So we do this sanitization process, and we wrap the containers in a greenhouse and let it stay for 30 days. So we monitor all the temperatures, and we need to keep it above 70 degrees for 30 days. In Vermont, we have a very short window of summer that we can make that happen, but that's how we're doing it. That's one of our methods. And our second method is pasteurization. This is our very first year of doing a solar pasteurizer with a 50-gallon container. It took about a day and a half to make that reach the temperatures that are necessary, 158 degrees for 30 minutes. So the second year, we added automation, and you could just push a button rather than pumping each time. And this year, we are building a new pasteurizer. It's going to be a mobile urine pasteurizing unit. It'll have a heat exchanger on it and be able to pasteurize 1,500 gallons of urine a day. And the nice thing about this, it's a 10-year permit that our state is going to be giving to us. And we will be able to go anywhere in Vermont, anywhere where people have learned to collect the urine and get it to a farm. We can arrive with this new piece of equipment that we're building and pasteurize it, and people can legally and safely put it on their fields. So that's the temperatures that we monitor in that pasteurizer. And then at the Rich Earth Institute, we are doing all kinds of field studies. Part of our niche in this whole conversation is to work with our farmers to see what will make it possible for them and what will make it easy for them to do this. So we take lots of soil samples, send them, many of them come to the University of Michigan. This is a study that we did with the USDA and to study dilution rates. How much water do we need to add to the urine when we put it on hay to make it safe for the hay so that it doesn't burn the roots. And we've done that for 3 years and have great statistical data at this point, and we're really pleased to say that you don't have to dilute the urine at all, that it does not burn the roots of the hay. And that's significant for farmers because they don't want to be carrying extra water around their fields. We always compare our plots to chemical fertilizers for controls, and this is our very special custom-made urine applicator. That grass looks a little more yellow than really it is. It's really green. But that's our first year, and that slide, we still continue to use it just to show you some pretty dramatic results. This center line has the urine, the middle one no urine, and the one on the end has half as much urine applied at that time. So we do all kinds of analysis. We weigh every bale of hay. We send forage samples away to find out how it impacted the forage quality of the hay. And here's some of our results, our yield studies here. We chose to work with hay first because for people thinking about recycling urine, the idea is sometimes difficult for people to get comfortable with. So because this is not something we ingest, humans don't ingest hay, which is for animals. So we started there and realized that was what people were comfortable with. But then to get to the part of why we're working with the people, all of you at University of Michigan, the pharmaceuticals in sewage, all of those things are high. Pathogens, heavy metals, industrial household chemicals, all those things are present in sewage. But in urine, you don't have most of those, but you do have the pharmaceuticals. So that's where in your body, that's where they go, and so we need to deal with that. So here we are in our 2-year study with the University of Michigan, funded by the EPA, and we're tracking the fertilizer, we're tracking the pharmaceuticals in the urine as it goes to the soil, the groundwater, and the harvested crops, and we are growing edible plants, lettuce, and carrots. So here's how we did it. Here's our urine collecting toilets, which you had 2 of on campus today. I don't know how many of you got to go and pee in our pee-only toilets today. How many of you did? Yay, thank you very much. You're contributing to some very important research. Some of your team came and visited us last year in Vermont to help prepare the samples after the collection event in Brattleboro. And this is the list of drugs and analytes that we have to be following. These are lysimeters, which we have buried in the ground, and they capture the groundwater. It's a simulation, and the rainwater goes through, and we can pump out through these white tubes on the side. So we've planted lettuce, and I'm fertilizing there with several different treatments, and we've been able to follow all those things. So here's our harvesting of the lettuce. We're very careful about how we did that, and we sent some frozen samples here to the labs, and to Buffalo, where they are doing the chemical analysis, and here for the biological analysis. So the Rich Earth Institute has a lot of next steps. We have a lot of things we want to do. There's the more we talk to people, the more studies we want to complete. We think in terms of engineering, some really critical things are to improve the toilet fixtures. We're getting there. There's new evolution coming along, like we said, with the plumbing codes that we helped develop. We left a wide band of opportunity for people to experiment within those codes, but that code is available for plumbers and architects. And then we are working on ways to lower the volume of the urine, because the transport is really a critically compromising cost to make this effective. So we're looking at reverse osmosis, which we started about 8 days ago in Vermont, and evaporation and distillation as well. So I just want to end our part of this to say that we are very inspired by Buckminster Fuller, who many of you know said pollution isn't anything but the resources we're not harvesting. And we allow these resources to disperse because we have been ignorant of their value. And I think that really applies to urine and human waste, which we like to say is a resource. So, thank you. Thank you.
Starting to recognize that you can actually place yourself in a computer-generated world and interact with it in a physical sense. I think this technology is just gonna blossom in the future.